Hello dear students, welcome to Teja my YouTube channel. So in this session we are going to discuss about one more topic, that is Gauss law in electrostatics. Yes, of course, in the last video also we have discussed about Gauss law, but we have not discussed much about the continuous charge distribution. So let us discuss about that here. So we have linear charge distribution, surface charge distribution and volume charge distribution. We'll go one by one. So before that, what is Gauss law? So Gauss law in electrostatics states that the total electric flux through a closed surface is equal to 1 by epsilon naught times charge enclosed. That means flux depends on the enclosed charge, where Q is enclosed charge. That's why I can write phi is directly proportional to enclosed charge. So what do you mean by enclosed charge? The charge which is present inside the Gaussian surface. So if you consider this is the surface in which how many charges are there? Let's consider Q1, Q2, Q3. Outside also we have Q4, Q5, all these charges. The flux depends on the enclosed charges Q1, Q2, Q3 only. So the flux through the, what is this? The surface, given surface here is equal to closed integral of E dot ds, which is equal to Q by epsilon naught, where Q is the enclosed charge and electric field here, which depends on all the charges. Do you remember? Electric field here depends on all the charges, but Q is just the enclosed charge. So, and then we have Q by epsilon naught. What is epsilon naught here? Epsilon naught is the absolute permittivity, and its value is given by epsilon naught is equal to 8.854 into 10 to the power minus 12 units. You can write farad per meter, or in terms of electrostatics first chapter, in terms of force, in terms of Newton and Coulomb also you can write the units. So this is the standard unit value in SI unit. Okay, next we have the derivation. If you want, please check in the description. I have given the link. You can just follow it for the derivation. Here I'm just giving you the final formula. The electric field due to uniformly charged infinite straight wire is, so here we have uniformly charged infinite straight wire where the charge density is lambda. What is charge density lambda? That is linear charge density, that is given by charge per unit length. So due to this linear charge, what is the electric field at a radial distance? Okay, where we are considering the Gaussian surface, and then we derive the expression for electric field, Gaussian surface. So what is the electric field along the radial distance? So that is given by lambda divided by 2 pi epsilon naught into r. R is missing here. R is the radius of this Gaussian cylinder. So lambda divided by 2 pi epsilon naught into r. Okay, this can also be written as E is equal to 2 lambda divided by 4 pi epsilon naught into r. What is 1 by 4 pi epsilon naught? K. So 2k lambda by r also you can write. Okay, in vector form we write n cap. N cap is the unit vector. Clear? So here electric field decreases with the distance. That's why it is given. So E is inversely proportional to R. Lambda is the charge density. K is 1 by 4 pi epsilon naught. Its value is, what is the value of 1 by 4 pi epsilon naught? K is equal to 1 over 4 pi epsilon naught. Its value is 9 into 10 to the power 9 in SI unit. Okay, in SI units, but its value is 1 in CGS unit. CGS unit. Its value is 1 in CGS unit and 9 into 10 to the power 9 in SI unit. Okay, do remember? Next, we have electric field due to uniformly charged infinite plane sheet. Here we have infinite plane sheet with surface charge density sigma. Okay, so there will be electric field on both sides. This electric field is given by sigma divided by 2 epsilon naught. In terms of unit vector, if you want, you can write E is equal to sigma by 2 epsilon naught into n cap. Then what is sigma here? Sigma is surface charge density, that is given by Q by A. A is the area that you can consider. So you can consider for small area also. So for small area, sigma is given by dq by dA. Clear? Yes. Then we have electric field due to uniformly charged solid or hollow sphere, especially conducting sphere. Let's consider conducting sphere. It may be hollow sphere or solid sphere. So electric field at a distance r outside the sphere. For this also derivation will be given in the link. Please follow it for the derivation. So E is equal to 1 by 4 epsilon q by r square. This is outside at a distance. For example, here we have sphere at this particular distance, that is r from its center. So r is taken from the center to the point P. At this point, electric field is inversely proportional to r square, because E is equal to 1 by 4 pi epsilon q by r square. So we have E is inversely proportional to r square. But if you consider on this sphere, okay, on this sphere, electric field is inversely proportional to capital R square. Okay, because small r becomes equal to capital R. So if you substitute, you will get E is equal to 1 by 4 epsilon q by r square. This is the maximum electric field. What is this? Maximum electric field. And inside, since the enclosed charge is 0, charge enclosed inside the surface will be 0, because whenever you give charge to the sphere, electric charges resides on it, because it is a conducting sphere. Since it is a conducting sphere, it's a conducting sphere, so E is inversely proportional to R square. So here we have electric field formula, E is equal to 1 by 4 epsilon q by R square. So inside it is 0. So charge enclosed inside is 0. So electric field is 0. And in second chapter, you will learn that electric potential is constant inside the sphere. Okay, we'll discuss about that in the second chapter. Next, we have solid sphere. Let's consider the charge is uniformly distributed inside the solid sphere, especially this is non-conducting. Charges doesn't move. Conducting. Okay, non-conducting sphere in which charge is there. Then actually there is no derivation for this in PU board level, but you can just learn the synopsis. Derivation you can do. Here I'm just giving it a direct formula, that is inside the electric field, inside the sphere, non-conducting sphere, electric field is directly proportional to R. E is directly proportional to R. That's why E is equal to rho R by 3 epsilon naught. And on the sphere, E is given by 1 by 4 epsilon naught q by R square. And outside the sphere, you just have to replace capital R by small r. So it is inversely proportional to R square. So the maximum electric field you can see on the surface again. So we'll get a linear graph. Inside, on it is maximum, outside it is inversely proportional to R square. Clear? Then, so that is given here. Next, electric field between the uniformly charged plates. Let's consider this plate is uniformly charged. So this plate is having positive charge, which gets uniformly distributed here. And if you give negative charge to this, so here we have negative charge. Now what is the electric field between these two plates? Okay, so here let me consider region 1, region 2 and region 3. At region 1 and region 2, electric field will be very negligible. There will be electric field, but it will be very negligible. So we consider that electric field is 0 here and electric field here is 0. But electric field here is given by electric field due to positive charge sigma by 2 epsilon naught and negative charge sigma divided by 2 epsilon naught. If you add these two, E is equal to 2 sigma divided by 2 epsilon naught, that is equal to sigma by epsilon naught. So this is about this. Okay, what if we have 3 plates? We'll discuss about that at the end of the video. Here we have some questions based on this. The total electric flux through the closed surface. Let me consider a closed surface here. The flux through this depends on what? The flux through the closed surface depends on charge enclosed. That's why we have the option C, that is net charge enclosed. Okay. Next, electric field inside the hollow spherical conductor is. Electric field inside the hollow spherical conductor, 0. Just now we have learnt. If you consider a different shaped object also, look at this, electric field is 0 inside the hollow conducting sphere or a conductor. That's why option B is correct. Then we have electric field intensity at a distance r from the infinitely long thin straight wire is. Straight wire, if you consider, electric field is given by lambda divided by 2 pi epsilon naught into r. So electric field is inversely proportional to r. So option B is correct. Next we have electric field near a infinite thin non-conducting sheet of surface charge and sigma is, just now we have learned, that is sigma divided by 2 epsilon naught. Clear? Then we have SI unit of electric flux. Since electric flux is given by E dot A, so for electric field, the unit is Newton per coulomb and area is meter square. That's why Newton meter square per coulomb is the unit. Is it given? Newton meters? No, it is not given. Newton meter per coulomb is given. So in terms of potential, if you write, electric field is given by volt per meter into area meter square is there. So another unit is volt meter. Do we have this unit here? Yes, volt meter. So option C is correct. Next we have electric field at the surface of a charged conductor is. So if you consider a charged conductor, so just a minute. Okay, let me consider a sphere here like this. So this is a charged conductor. Okay, so for a charged conductor, electric field on the surface will be perpendicular to the surface. At this particular surface, it will be perpendicular. So here it is given normal to the surface. Electric field at the surface of the charged conductor will be always normal. Theta will be 90 degree. Even for what is that? Equipotential surface also, it is perpendicular. Okay. Next, the net flux through a closed surface is 0. Then, so if you consider through the, why does it happen? Okay, if you consider this is the closed surface, if the flux through this surface is closed surface is 0, that means what? Q by epsilon naught. Q by epsilon naught. That is, Q is also 0. That's why net charge inside the surface also must be 0. Because flux is 0, then charge must be 0. Then inside the uniformly charged non-conducting solid sphere, the electric field is non-conducting sphere. So electric field is directly proportional to R. That's why option C is correct. Next we have dimensions of electric flux. So electric flux is given by E into A. Can I write electric field is given by F by Q? Okay, in the first Coulomb's law concept I have explained it, please learn it. So F by Q. So force can be written as, the unit of force is kg meter per second square, and area it is meter square. For charge can be written as current into time. Okay, so if you write for time seconds, current ampere, this gives kg, it is m power 1. Meter, we have meter into meter square is meter cube. Time divided by second is there, t power minus 3, and ampere power minus 1. So this is the dimensions m1 l3 minus 3 minus 1. Option 1 is correct. Okay, next, moving on to next one. A point charge. For point charge, most appropriate Gaussian surface is sphere. If you consider a point charge, so you can consider the sphere around it. So sphere is the best Gaussian surface for point charge. So option C is correct. Next we have, if dielectric constant K is placed in the vacuum, the flux from the enclosed charge is, since phi depends on E into A, electric field is inversely proportional to what is this dielectric constant? So we write E divided by K into A. So that will be phi divided by K. So flux in a medium is inversely proportional to K. So that becomes 1 by K times. Next, we have work done in moving a charge on the surface of the Gaussian sphere surrounding the point charges. Since Gaussian sphere is having the uniform potential in it, so the work done in moving a charge on the sphere, so there will be equal potential at all points. So work done is given by final potential minus initial potential into the charge which we are moving is q. So final potential, initial potential same, so we'll get 0. So work done will be 0 if it is spherical in shape. If it is different shape, so we may have to consider different case. Then 8 dipoles plural of charges of magnitude plus or minus q. So dipole means 1 plus 1 minus charge will be there. So the net charge will be 0. Like this, 8 dipoles are there. 8 dipoles. So net charge will be 0 only. What will be the total flux through the cube? So here I am considering the cube. Let's consider just the closed surface. So through this closed surface, what is the flux? 0, because net charge is 0. Next MCQ type question. The flux of electric field to these charges through the surface is. So since the surface consists of a positive and negative charge of equal magnitude, so therefore they get cancelled, flux will be 0. Outside charge not considered. Then we have the flux for Gaussian surface A. A is outside surface and B is inside surface. We have 3 charges here. So the electric flux for Gaussian surface A that enclose the charged particles in free space is, that is given, Q1 is minus 14 nanocoulomb, Q2 is 78 nanocoulomb, and Q3 is 58 nanocoulomb. So charge enclosed is given by Q1 plus Q2 plus Q3 is equal to Q1 is minus 14 nano means 10 to the power minus 9 coulomb plus Q2 is 78.85 nano means 10 to the power minus 9 coulomb, and Q3 is minus 56 into 10 to the power minus 9 coulomb. So if we add, you will get 56 plus 14 is minus 70 into 10 to the power minus 9 and plus 78.85 into 10 to the power minus 9 coulomb is there. So if you subtract 78.85 minus 70 is 8.85 into 10 to the power minus 9 coulomb. So this is the charge enclosed. What they are asking, electric flux. Electric flux in terms of charge is given by Q by epsilon naught. Okay, Q by epsilon naught. So what is Q? Just now we have found, that is charge enclosed is 8.85 into 10 to the power minus 9 divided by 8.85 into 10 to the power minus 12, which is equal to 8.85. 8.85 get cancelled. 10 to the power 12 minus 9 is 10 to the power 3. So that is option B is correct. Clear with that? Yes. Moving on to next one. A Gaussian surface is shown in the figure. The electric field on the surface will be, so here depends on Q1. No, here it is given electric field, not electric flux. Depends on both Q1 and Q2. So that is due to all the charges. Next, the electric field due to uniformly charged non-conducting sphere of radius r as the function of distance from its center is given by. Since electric field depends on r as directly proportional to r if r is less than r, so electric field is inversely proportional to r square when r is equal to r. So electric field is inversely proportional to small r square when r is greater than r. Therefore we'll get a graph B. Okay, B is the correct option. Next we have a charge q is distributed uniformly on a sphere. So if you consider a sphere here, then the electric field at any point r less than 0 is, Actually here solid sphere is given, but they have not mentioned whether it is conducting or non-conducting. Let us consider it is non-conducting sphere. Non-conducting sphere. For non-conducting sphere, electric field is directly proportional to R. So that's why I'll go with option C. Then we have, correct, no? Yeah. Next. Two parallel large thin metal sheets have equal surface charge densities of opposite sign. So charge density is given sigma. The electric field between the plates is. So for electric field between the two plates, I have given you the formula, that is sigma by epsilon naught. Sigma is 2.56 into 10 to the power minus 11 divided by epsilon naught is 8.85 into 10 to the power minus 12. So which will come around 3 Newton per coulomb. 2 point something will come, 2.9 or 2.8 something, which is almost equal to 3. Not exactly equal, almost equal to 3 Newton per coulomb. So option C is correct. Then we have 3 large metal parallel plates have the uniform surface charge densities as shown in the figure. So due to positive plate, electric field is inverse, that is given by E1 is equal to sigma divided by 2 epsilon naught. Which direction? Along negative z axis, so we can write downwards. Next, E2 is equal to minus charge is there, so minus 2 sigma divided by epsilon naught. So minus is not because this charge density is negative, but because it is downwards, so I will keep minus as it is downwards. So minus sign indicates that electric field is opposite to k cap. E3 is again downwards, E1 is also downwards, E2 is also downward, because electric field is away from the positive charge towards negative charge. So due to negative charge, both the negative charges are downwards, so electric field will be downwards only. Positive charge downwards because it is away. So you may have to add all this. If you add all this, here 2 will come, again negative k cap. So here net electric field is E1 plus E2 plus E3 is equal to minus sigma by 2 epsilon naught minus 2 sigma by 2 epsilon naught and minus sigma by 2 epsilon naught, that is minus 1 2 3 4 minus 4 sigma by 2 epsilon naught. So answer will be minus 2 sigma divided by epsilon naught. So this is about this. This is the electric field at point P, which is below positive plate, above negative plates. So this will be the answer. So this is about this video, dear students. So I have completed the chapter electric charges and fields. Now I'll move on to electric potential, wherein I'll be giving you the detailed synopsis for KCET level, and I will be solving some easy questions based on it. We'll try to solve PYQs and difficult level questions in the coming videos. If you feel the content is useful, please share it to your friends and try to support this channel for more content. Thank you so much.